Slither has an ERC conformance tool called Slither Check ERC, which checks conformance for various ERC standards such as ERC 20, ERC 721, 777, 165, 223, and finally 1820, some of which we have discussed in the Security 201 module. Examples of these checks are to see if functions are present, return the correct type, have view mutability, and if events are present, emitted, and parameters of such events are indexed as per the ERC spec. This is again handy for consolidating all ERC specific checks into one single tool. And finally, Slither also has a property generation tool called slitherprop, which generates code properties or invariants that can then be used for testing with unit tests or echidna, and completely automatically. The ERC20 scenarios that can be tested with this tool are things like checking for correct token transfer, the possible functionality, or that no one can incorrectly mint or burn tokens. Besides the various detectors, printers, and tools of Slither that we just discussed, Slither also supports an extensible architecture that allows one to integrate new detectors into the tool. The skeleton for such a detector implementation has things like arguments, help, impact, confidence, and link to the wiki for that detector, and finally a placeholder for the most important part of the detector logic itself. This extensible architecture can help with creating application-specific detectors, and also enables the community to contribute new detectors to the Slither codebase. So those are all the Slither features that we're going to cover here. And as we see, it is an extensive tool with support for 75 plus detectors and multiple other helpful features as well, for reasons of which it's widely referenced and used across projects in the space. Let's now move on to another tool from Trail of Bits called Manticore, which is a symbolic execution tool. This again helps with analysis of Ethereum smart contracts and complements Slither. Manticore can execute a program with symbolic inputs and explore all possible states it can reach. It can automatically produce concrete inputs that result in any desirable program state. It can detect crashes and other failures in smart contracts, provide instrumentation capabilities, and finally a programmatic interface to its analysis engine via a Python API similar to Slither. Another tool from Trail of Bits is Echidna, which is a fuzzing tool and complements Slither and Manticore, again for use with smart contract audits. This is written in Haskell, and it performs grammar-based fuzzing campaigns based on a contract's ABI to falsify user-defined predicates or even solidity assertions in the smart contract code. Echidna has many notable features, such as it generates inputs tailored to the actual code, has an optional corpus collection of predefined campaigns. It supports mutations and coverage guidance for deeper bugs. It can be powered by the slitherprop tool to extract useful information before the fuzzing campaign. It has source code integration to help identify which lines are covered after the fuzzing campaign. It has support for multiple user interfaces, automatic test case minimization for quick triage, and finally seamless integration into the development workflow, among other things. As for Echidna's usage, I would recommend looking up Echidna's documentation and available tutorials on TrailorBit's website for such details. But at a high level, the usage involves three aspects. First one is executing the test runner, where the core echidna functionality is part of an executable called echidna test that takes a contract and a list of invariants as inputs. For each invariant, it generates random call sequences to the contract and checks if the invariant holds. If it can find some way to falsify the invariant, it prints the call sequence that does so. And these are typically referred to as counterexamples in this terminology. If it can't find counterexamples, then we have some assurance that the contract is safe with respect to that invariant. The second aspect is that of writing invariants. Invariants are expressed as solidity functions with names that begin with echidna underscore. They have no arguments and they return a boolean. And the third aspect is that of collecting and visualizing coverage. After finishing a fuzzing campaign, echidna can save that coverage maximizing corpus in a special directory which will contain two entries. A directory with JSON files that can be replayed by echidna later, and a plain text file that contains a copy of the source code with coverage annotations. TrailorBits has combined the three tools we just discussed into a tools package, which is a Docker container package called ETH Security Toolbox, where they are pre-installed and pre-configured. And as you can imagine, this makes it very handy and very easy to start off with using these tools. So the ETH Security Toolbox has Slither, Echidna, and Manticore, and besides these three also has Rattle and Ethanol tools, which we will touch upon in coming slides. Ethersplay is a binary ninja plugin from TrailorBits that enables an EVM disassembler and related analysis tools. For those who aren't aware, Binary Ninja is a widely used extensible reverse engineering platform which can disassemble a binary and display it in various ways. So Ethersplay effectively extends that to work with EVM bytecode. This takes EVM bytecode in raw binary format as input and generates a control flow graph of all functions. It can also be used to display manticore's coverage. PiEVM ASM is another security tool from TrailorBits, which provides an assembler and disassembler library for the Ethereum virtual machine, EVM. This includes a command line utility for doing the assembling and disassembling, and also includes a Python API for extensibility. Rattle is another security tool from TrailorBits. It is an EVM binary static analysis framework that is designed to work with deployed smart contracts. It takes EVM byte strings as inputs and uses a flow-sensitive analysis to recover the control flow graph. In static analysis terminology, flow sensitive refers to an analysis that considers the control flow statements. Similarly, there is context sensitive and path sensitive analysis as well. Rattle further converts the control flow graph into a single static assignment form or SSA form with infinite registers and optimizes this SSA by removing stack instructions of dupes, swaps, pushes, and pops. Recall that EVM is a stack-based machine, and so there are typically many such stack instructions in the bytecode as operands are pushed onto the stack and results are popped. Rattle, by converting the bytecode instructions from a stack machine to SSA form, removes more than 60% of all EVM instructions. And because of that, it presents a user-friendly interface for analyzing smart contract bytecode. For anyone interested in programming language analysis, I would encourage them to look up these concepts of SSA and sensitivity and so on. PiEVM cfgBuilder is another tool from TrailerBits. This is used to extract a control flow graph from EVM bytecode. This tool helps us reliably recover a control flow graph or CFG from the EVM bytecode and also recovers function names and their attributes such as payable, view, pure, etc. It outputs the CFG to a dot file. And this EVM cfgBuilder tool is used by Ethersplay, Manticore, and some of the other tools from TrailerBits. CriticCompile is another tool from TrailerBits. It is a smart contract compilation library that is used in the security tools from TrailerBits. It supports Truffle, Embar, Etherscan, Brownie, Waffle, Hardhat, and other development environments. And this plugin is used in the Critic family of tools from TrailerBits that includes Slither, Echidna, and Manticore. Select is a security helper tool again from TrailerBits, and this is a script that is used to quickly switch between different Solidity compiler versions. Select manages installing and setting different Solidity compiler versions using a wrapper around Solidity, which picks the right version according to what was set via Select. Solidity compiler, the Solidity binaries are downloaded from the official Solidity language repository, and this tool is very helpful while analyzing different smart contract projects because there is often a need to switch between different Solidity compiler versions depending on which version is being used by the project that is being analyzed. So this tool is very handy in such situations and helps us work with other security tools that depend on the Solidity compiler version. Ethanol is a testing tool referred to as the Ethereum testing Swiss Army knife, again from TrailerBits. It's a JSON RPC multiplexer analysis tool wrapper and test integration tool all bundled into one. For multiplexing, it runs a JSON RPC server that can multiplex calls to one or more Ethereum clients with an API for filtering, modifying such JSON RPC calls. It enables differential testing by sending JSON RPC sequences to multiple Ethereum clients and further helps with the deployment and interaction with multiple networks at the same time. For the analysis tool wrapping part, it provides a JSON RPC client for advanced analysis tools such as Manticore, which makes it much easier to work with such tools because there is now no need for custom scripts for those tools. And for integration with test frameworks such as Ganache and Truffle, it helps run a local test network with a single command and enables the use of Truffle migrations to bootstrap Manticore analysis. So for all these reasons, it is referred to as the Swiss Army knife for Ethereum testing. Now moving on to tools from consensus diligence. Mythics may be considered as their flagship tool. Mythics is a powerful security analysis service that finds vulnerabilities in Ethereum smart contract code during the development lifecycle. It's a paid API-based service that uses several tools in the backend, and these include Maru, a static analyzer, Mithril, a symbolic analyzer, and the third one being Harvey, which is a gray box fuzzer. And in combination among these three tools, Mythics implements a total of 46 plus detectors for now. While Maru and Harvey are closed source as of now, Mithril is open source. And we'll talk more about different aspects of Mythics in the forthcoming slides. So how does the Mythics process work? Recall that Mythics is an API-based service, so Mythics does not run locally on the user's machines, but it runs in the cloud. So the first step is for the project to submit the code to the Mythics service. The analysis requests are encrypted with TLS, and the code one submits can only be accessed by them. And one is expected to submit both the source code and the compiled bytecode of the smart contracts for best results. The second step is to activate the full suite of analysis techniques behind Mythics. And here, the longer Mythics runs, the more security weaknesses it can detect. And this is because the precision of the symbolic, checker, and the fuzzing components of Mythics can get better with more iterations. The third and final step is to receive a detailed analysis report from the Mythics service. And this report lists all the weaknesses found in the submitted code, including the exact location of those issues. And these reports that are generated can only be accessed by the submitter. Mythics here offers 3 scan modes: quick, standard, and deep, for differing levels of analysis depth, and provides a user-friendly dashboard for analyzing the results returned. Now let's talk about the tools used by the Mythics service. When a project submits their code to the Mythics API, it gets analyzed by multiple microservices in parallel, where 3 tools cooperate to return a more comprehensive set of results in the execution time decided by the type of scan chosen. The first of the 3 tools is a static analyzer called Maru that parses the Solidity AST for the project. The second tool is a symbolic analyzer called Mithril that detects all the possible vulnerable states in the contract. And finally, the third tool is Harvey, which is a gray box fuzzer that detects vulnerable execution paths in the smart contract. Compared to traditional black box fuzzing, gray box fuzzing is guided by coverage information, which is made possible by using program instrumentation to trace the code coverage reached by each input during fuzzing. So these 3 tools are used in combination by the Mythics service to provide a comprehensive analysis of the vulnerabilities within the smart contract being analyzed. The coverage that is provided by Mythics extends to most of the smart contract weaknesses found in the Smart Contract Weakness Registry, referred to as the SWC registry, which we will talk more about in one of the forthcoming slides. And this comprehensive coverage addresses 46 plus detectors as of today. Mythics is based on a security as a service or SaaS platform, with the premise that this SaaS approach is better because of 3 main reasons. The first reason is that with this approach, one can expect higher performance compared to running the security tools locally, because the compute power in the cloud is typically much higher than what may typically be expected at the user's end on a laptop or a desktop. And the second aspect is that we can expect a higher vulnerability coverage with 3 tools than running any single standalone tool. The third benefit is from continuous improvements to security analysis technology, with new or improved security tests, methodologies, and tools that can be adopted as the smart contract security landscape evolves, with different types of vulnerabilities and exploit vectors emerging as the compiler revisions change, new coding patterns emerge, new dependencies start getting used, new protocols start getting used, and even the Ethereum protocol upgrades over time. So for these three reasons, the SaaS or API based approach of Mythics is considered as being better than running any one of those tools locally on the user's end.